Hello everybody. Having done some videos on problems on source transformation, mesh current analysis, and problems on networks consisting of coupled circuits, etc., I thought of taking up node voltage analysis as my next topic for my videos. Here again, I have not taken conventional problems of writing the nodal equations and solving for the unknowns. Instead, I have taken up a problem which is slightly tricky, in the sense that in the problem which I am dealing right now, I am supposed to determine the value of V for a certain specific network conditions. Now you are supposed to find out the magnitude of the source that has to be applied to the network so that a certain condition is met in the network, and it can be done using nodal analysis. So if some problems of this nature are to be handled, how to do it, how do we go about it, is something that I thought I would make some videos on problems of this nature. Alright, so with that background, I will go ahead. So this is how the problem reads. You are supposed to find the voltage V, which makes the current through 10 ohm resistor 0. Okay, and the method suggested is nodal voltage analysis. Well, let's see how to do this particular problem. So nodal voltage analysis, normally, people tend to convert the voltage source into current source and then go ahead with the problem. So either ways, you can retain the voltage source as it is and go ahead with the problem, or you can convert the voltage source into current source and then do the problem. So we'll try to see both the things. Okay, so both the methods I'll try to cover up here in this particular problem. Okay, so I will try to identify the nodes in the problem. Okay, so if I have to maintain the voltage sources as it is, how many nodes can be identified? If I am right, there can be a node here, there can be a node here, here. All these green dots I am marking are the nodes. This is one common node. Okay, so I am able to see 5 nodes, out of which the node that is common to all the elements, like in most of the elements, and one end of the source, I intend grounding. This is my datum node. Okay, so out of the total nodes, one of the nodes, whichever is convenient, is made the datum node. Okay, now with respect to this datum node, if I need to designate the potentials of various nodes with respect to the datum, this particular terminal is at, this particular node is at capital V volts. Okay, and I will designate this particular terminal, node voltage, to be VA, and this particular node voltage to be VB, and with respect to ground, the voltage of this particular, the potential of this node is plus 50. This is plus V. Alright, so now I will write the equations by inspection. I can do that. I will be able to write the equations by inspection, or I can use the first principle, whichever way. Suppose let me try by first principle only. For most of the students, first principle is easy to understand. I will try to take the current in this particular path to be this way. This is the current in this direction, the current in this particular element to be flowing in this direction. Okay, and I'll try to write the equation, and here again in this thing I will try to write the currents. Okay, so I will try to write the KCL equations at node A, which has a potential of VA. How do I do it? Okay, so at KCL equations, because the basis for node voltage analysis is KCL. KCL equation at node A. At node A, if I have to write, the incoming current is V minus VA divided by 3. Okay, V minus VA divided by 3. It's like this. This is 3 ohm. This is plus V and this is VA. The current is flowing from higher potential to lower potential. What is the magnitude of current? The magnitude of current is the difference in potential, that is V is at a higher potential, VA is at a lower potential. The difference in the two potentials will give me the potential difference divided by the resistance is the current. Alright, extending the same logic, this is the incoming current at node A. The two outgoing currents can be written as equal to, the other current is VA is the potential VA minus 0 divided by 2. This is the current through 2 ohm resistance. Okay, and the other current is now VA minus VB. This is plus VA minus VB divided by 10. This is the simple KCL equation. Now if I rearrange, if I group the terms, all the VA terms and VB terms, if I group, I'll be able to write the equation to be equal to, I'll collect all the terms with VA as the coefficient. I'll write it as 1 by 3 plus 1 by 2 plus 1 by 10 whole thing into VA minus 1 by 10 into VB. This is equal to V by 3. Alright, this is one simple equation. Okay, even if we convert this voltage source into equivalent current source, then how do we get it? We get it like this. We get this source as, this is the current source with the magnitude of V by 3, and I'll get this 3 ohm across. This is how the conversion of voltage source to current source happens. Alright, now you will end up getting the same equation. Even if you convert this voltage source to a current source of this nature, you will end up arriving at the same equation. Okay, so either ways it is the same equation. The methods may be different, but then the result is the same. Okay, so having obtained this equation, we will try to go ahead with the other equation. Okay, so if this equation we could have written by inspection. Now at node B, we will try to write it by inspection. Okay, so node equation or nodal equation, whichever way we call it, nodal equation at node B. Okay, the first one we wrote it by first principle, by inspection we will write. How do we write by inspection? So it is the element that is common between node B and node A is to be taken with a negative sign. That means it is minus VA times the admittance or the conductance in this case, that is 1 by 10, and plus at node B sum of all the admittances meeting at node B. How many admittances are there? In fact, 10 ohm, 7 ohm, 5 ohm resistances are connected to node B. So if I have to write the admittances, I will write it as 1 by 5 plus 1 by 10, and the other one is 1 by 7. These are the admittances meeting at node B into VB. This should be equal to the current that enters the node. What is the current that enters the node? It is 50 by 7. If you convert it into a current source, it is 50 by 7. Alright. As a side note, I'll show you. It is like this is 7 ohm. This is my 50 volt. This is 50 volt and this is 7 ohm. If I convert this into a current source, it becomes simply 50 by 7 amperes of current will be pumped out of the source, and this source has got 7 ohms across. Okay. So you can convert it into a current source and do it, or you can retain the voltage source as it is, and you can do it. The convenience depends on the individuals. Okay, so we wrote the second equation by inspection. Okay, so this is my first equation. I'll try to number the equation now. This equation is equation 1 and this is equation 2. Okay, now we will try to see what is the problem statement. Going back to the problem statement, it says find the value of V, which makes the current in 10 ohm resistance 0. That is what is being given. Okay, so we will put it mathematically. We will try to express the given statement in the form of an expression. What is given? Given the current through 10 ohms. How do we determine the current through 10 ohms? The difference in potential across 10 ohms, that is VA minus VB, the potential difference, divided by the resistance. This should be 0. The given statement is now converted into a mathematical expression, which goes to say that if I cross multiply, I will get VA minus VB equal to 0, or VA equal to VB. Okay, it's as simple as that. Now I know what we have to do. We need to equate VA and VB. So we have two equations. We can write what is VA. What is VA? If I write the expression for VA, I can write VA as equal to the ratio of two determinants. What are those determinants? The ratio of two determinants. This is what is VA. The two determinants are, this is your delta determinant. We call this delta. We need not have to evaluate delta, but still let me write delta. So the delta is written as, I will write this line later. This delta determinant is given by, I have not simplified, I'll write it as it is, 1 by 3 plus 1 by 2 plus 1 by 10. This is the coefficient of VA from first equation. Okay, and or else I'll give you the simplified version. This ratio comes out to be equal to 0.93. What I mean is equation 1 is this is 0.93. 0.93 I will get it as 1 by 3 plus 1 by 2 plus 1 by 10 will come out to be 0.93, and this is minus 0.1. 1 by 10 is 0.1 and this is minus 0.1, and this comes out to be 0.443. Alright, that is 1 by 5 plus 1 by 10 plus 1 by 7 results in 0.443. We can always compute. You have scientific calculators which will do that work for you, so we need not have to bother. Okay, and this is what we call as discriminant delta. Okay, now I will try to write the numerator of VA. How do I write the numerator of VA? I replace the first column of delta by V by 3 and 7.143. So that is the right hand side of the two equations, equation 1 and equation 2. This is equal to 7.143. This is my equation 2. Okay. and the second column is retained as it is 0.443 of delta. This is my VA. And what is VB? VB is written as the ratio of two determinants. The denominator is delta and the numerator is obtained by numerator determinant is obtained by replacing the second column of delta by the right hand side elements of equation 1 and 2. Okay, that comes out to be, this is my delta as it is 0.93 minus 0.1 minus 0.1, 0.443. In fact, we are not interested in evaluation of delta. I'm writing it because you need to understand these things. Otherwise, we need not have to bother about these things. This is 0.93, this is minus 0.1. Now, the second column is replaced by V by 3 and 7.143. Okay. So, we can evaluate, this is how we get the expression for VA and VB. Of course, we cannot evaluate VA and VB because V is not known to us. That is what is to be determined, right? So these are the two things that we have. Now, we will put this in equation 3. We will call this equation 3. We will try to substitute the value of VA and VB in equation 3. What will happen? Let's try to write equation 3. If I have to write that, my determinant V by 3 minus 0.1, 7.143, 0.443, this determinant, whole thing divided by the delta determinant. What is delta determinant? This is my delta determinant. This is equal to the VB. VB has got 0.93 V by 3 minus 0.1, 7.143 divided by delta. So, when I equate the two, my delta on both sides would get cancelled. This delta would get cancelled with this delta. Alright. Now, I will have to simply simplify and get the value of V. The only unknown is V. I will get, if I multiply, that is V by 3 into 0.443 plus 0.1. I am simply expanding the determinant. I am not doing any great mathematics here. It is simply the evaluation. This is equal to 0.93 into 7.143 plus 0.1 into V by 3. Alright. So, we have V on either side. If I can transfer V onto one side, I will get, and do the multiplication part, I will get this to be equal to 5.929, from which I will get V to be equal to 5.929 divided by 0.114, and if I simplify this, I will get V to be equal to 52 volts. Alright. So, it goes to say that if I apply 52 volts to that network, then there won't be current in 10 ohm resistance. So, we have solved this problem based on nodal analysis. We could have done it by mesh also. There is, you can do it by several ways, but then in this particular problem, the method that is asked is node voltage analysis, an elementary problem. This is a very simple problem because the network has only resistances. It is as simple as that. We wrote two equations by inspection. Of course, I didn't convert it into a current source. Even if you want to convert it into current source, then also it becomes simple. Okay, maybe I will before I wind up this particular video, I will give you the current source equivalent, so that viewers will not have any difficulty in understanding the things. Okay, I will try to take this network, and then that part we will try to do it. Okay, so I will take this network, I'll copy this down, then maybe I'll paste it here. I pasted it here. Now I'll try to do the conversion, source conversion. I remove these things, and let me do the source conversion, and let me see how the things come out to be. What I mean is, I will remove this. Okay, I'll try to take this back. No, this is much better, much easier. Okay, now what I do is, I will try to convert the voltage source into current source. Okay, so what will happen to my network, I'll see. Okay, I'll rewrite the network. Now I will get this line directly here. There is one more line here. This line is little not straight. Okay, now I am converting this source, the voltage source, into equivalent current source. How do I write? I will write the source. You would appreciate if I write the current source in this manner. The current source has the resistance coming across it. So the magnitude of this current source is V by 3 amperes, and the polarity of the current is upwards. Alright, and this resistance will be simply 3 ohms. This is 3 ohms. And the other current source, that is 50 volt voltage source, gets converted into an equivalent current source, which has the resistance of 7 ohms across it. This is 7 ohms, and I have my current source the value of this source is 50 by 7. So many amperes. I suppose it's simple, right? It is simple. Okay, we have converted the voltage source into current source. Now how to write the equation by inspection? At any node, we write node. There are only 3 nodes. One is the datum node, another are VA and VB. If I write by inspection, it is the first node, VA, into sum of all the admittances meeting at that node. Sum of all the admittances would mean 1 by 3 plus 1 by 2 plus 1 by 10 minus the admittance that is common between the 2 nodes, that's 10, 1 by 10, that is admittance, into VB, equal to current entering the node, that is V by 3. This is what is our first equation. Even in the previous case, you can always scroll back and see, rewind and see. Alright. Similarly, if I have to write the equation at node B, by inspection, what it says is the admittance that is common between the node A and node B with a negative sign, that is minus 1 by 10 into VA plus sum of all the admittances that meets at node B. How many admittances are there? There are 3. 1 by 10 plus 1 by 5 plus 1 by 7. This entire thing has to be multiplied with VB, equal to current entering the node, 50 by 7. Okay, so you can even retain the voltage source and do it, or convert the voltage sources into current sources and do it. So once the equations are ready, all you have to do is to apply the condition that for the current through 10 ohm to be 0, VA should be equal to VB, and we try to equate and get the result. Alright. So we can write the concluding statement. The problem has to be properly concluded. That's important. When V equal to 52 volts, there is no current. There won't be any current. There won't be any current through 10 ohm resistance. This is how the problem ends. Okay, so nodal equations can be written by inspection, either by converting the voltage sources to current sources or retaining the voltage sources. So I'll try to come up with trickier problems on node voltage analysis in my coming videos. Thank you for viewing. If you have any specific requirement, if you are interested in getting any problem solved, you can always post it, or any queries if you have. I'm too happy to attend to that. Thank you so much. See you in the next video.